Now let's quickly discuss two more definitions regarding norm before we move to the next topic, and a few properties related to these norms. First one is unitarily invariant norms. This is actually obvious from the name. So a norm is unitarily invariant if the matrix norm of A same as the matrix norm of, I think we've already discussed this, U, A, B. For all A belonging to Cn cross N, and unitary matrices V belong to Cn cross. The U and V are unitary matrices. The most common example is actually what do you call an L2 norm, right? L2 norm in the sense this is a unitary invariant norm. This is a spectral norm, right? Yeah, this is a spectral norm. Is it the spectral norm? Yeah, it's a spectral norm. Yes. Why is this unitary invariant? It's because okay, let's show this. Let's go back to okay. The lambda is eigenvalue if you have machine. Yeah. A Hermitian A something which we have to be careful here. Now look at it. It's one thing which we had to note down. So spectral norm is the root of rho of A Hermitian, right? This is the spectral norm of A. This is square root of A Hermitian A, I suppose, or A into a Hermitian, whatever. So we have U into A. This is pretty clear. Square root of rho of A Hermitian is U. Let's take the case of UA, then U Hermitian is A Hermitian, U Hermitian, UA, which is root of A Hermitian A, just same as the spectral norm of the spectral norm of the A, and this is spectral norm of UA. This we can prove easily. Oh, this is, yeah. Similarly, we can prove it for A into V as well. So there also it's true. Okay, this is how we can prove it's unitarily invariant. And now another definition is self-adjoint norms. A self-adjoint norm is, suppose the definition is, suppose we have, this is a matrix norm. Remember, okay, nothing. Remember, this is a matrix norm. This is a matrix norm on Cn cross n, then norm of A H, which is defined as the matrix norm of A Hermitian is also a norm. And if norm of A is equal to norm of A Hermitian, then it is called a self-adjoint norm. Let's look at few examples. One is vector norm. This is L2 norm of A. Okay. This is equal to norm of, this is again equal to norm of A2. Why? Because here we are just taking the squares of all terms and adding them together, right? And taking the root of them. Even if we transpose it, it doesn't make any sort of difference. We're just taking individual elements. So this is self-adjoint. Now let's take the another case where we have L1 norm, and this is again equal to, here the Hermitian norm is same as, I mean the norm of A Hermitian, L1 norm of A Hermitian is same as L1 norm of A. Here also we're taking the individual elements of the matrix, taking the modulus and adding them all together. Fine, they're same. Now let's look at the Frobenius norm. Oh, yeah, we've already seen Frobenius norm. Fine. Now let's look at spectral norm. Okay, spectral norm, self-adjoint of that. It's the self-adjoint norm of that, which is equal to the spectral norm of a Hermitian, which is spectral radius of, it's we're taking squares, so it's root of spectral radius. Okay, let's put the root. Root of spectral radius of a Hermitian, which is the same as square root of rho of a Hermitian A. So which is equal to the spectral norm of light. Why is this true? Now, eigenvalues of A Hermitian and eigenvalues of A Hermitian A are same. Can you say that? Both are symmetric matrices, right? A Hermitian A Hermitian and A Hermitian A are symmetric matrices. So both their transposes are the same. That means A and A Hermitian are same. You can just put it alternatively. Okay, so we've seen examples of self-adjoint, but we have to note that not all matrices are self-adjoint. For example, these two norms and this are not self-adjoint joint norms. In fact, the self-adjoint of maximum row sum, maximum column sum, we take the self-adjoint of this, is in fact the maximum row sum, and similarly, self-adjoint of maximum row sum is maximum column sum. Also, another important point to know, spectral norm. So these are induced norms, right? These are induced or operator norms. These are derived from vector norms. This is again the induced norm, which is induced from the vector norm. But spectral norm is induced just unitarily invariant, and also it's self-adjoint. In fact, it turns out that it's the only induced unitarily invariant and self-adjoint norm, which satisfies all these properties. Okay, yeah, let's conclude the discussion on matrix norms now. We'll move to the next topic in the next lecture.